lesson on rational numbers. A rational number is any number that can be expressed as a fraction p over q, where p and q are integers and q is not zero. Let's look at some examples of rational numbers. All integers are rational numbers because they can be written as fractions with denominator 1, terminating decimals like 0.5, and repeating decimals like 0.3 repeating are also rational numbers. Let's visualize some rational numbers on a number line. Here are some common fractions and their positions. Notice how rational numbers can be positive, negative, or zero. Now, let's learn how to perform operations with rational numbers. When adding or subtracting fractions, we need a common denominator. For example, to add 1/3 plus 1/2, we first find a common denominator of 6. For multiplication, we multiply the numerators together and denominators together. Let's multiply 1/2 times 3/4. For division, we multiply by the reciprocal. To divide 1/2 by 1/4, we multiply 1/2 times 4/1. Remember, rational numbers are all around us in everyday life. They help us represent parts of a whole, measurements, and many other quantities. Practice working with rational numbers to become more comfortable with these important mathematical concepts. Today we're going to learn about irrational numbers, what they are, their properties, and how they differ from rational numbers. Before we discuss irrational numbers, let's first understand what rational numbers are. A rational number is any number that can be expressed as a fraction p over q, where p and q are integers and q is not zero. Now, irrational numbers are numbers that cannot be expressed as a simple fraction. When written as a decimal, they go on forever without repeating. Let's look at one of the most famous irrational numbers, the square root of 2. If we try to calculate it, we get 1.414235, and it goes on forever without repeating. Here's a fascinating fact. We can prove that the square root of 2 is irrational. Let's assume it is rational. Then it could be written as p over q in lowest terms. Square both sides, and we get 2 equals p squared over q squared. Multiply both sides by q squared, and p squared equals 2q squared. There are many other famous irrational numbers. Pi is perhaps the most well-known, equal to approximately 3.14159. Another is Euler's number, which is approximately 2.71828. Let's visualize where these numbers live on the number line. Rational numbers can be plotted as exact points, while irrational numbers fill in the gaps between them. Together, rational and irrational numbers make up all real numbers. Irrational numbers appear frequently in nature and science. The ratio of a circle's circumference to its diameter is always pi. The number e appears in calculations involving growth and decay. And the golden ratio, another irrational number, appears in art, architecture, and nature. Remember, irrational numbers are just as important as rational numbers in mathematics. They help us describe the world around us with precision, even though their decimal representations never end. Welcome! Today we're going to learn about real numbers and their relationship with rational and irrational numbers. First, let's understand what real numbers are. Real numbers include all points on the number line, extending infinitely in both directions. This includes numbers like -5, 0, 3.14, and even the square root of 2. Let's start with rational numbers. A rational number is any number that can be expressed as a fraction p over q, where p and q are integers and q is not zero. For example, 1/2, -3/4, and 2 are all rational numbers. Rational numbers can also be expressed as decimals that either terminate or repeat. Now, let's look at irrational numbers. Irrational numbers are real numbers that cannot be expressed as a simple fraction. The most famous examples are pi and the square root of 2. These numbers have decimal expansions that go on forever without repeating. Let's visualize how real numbers, rational numbers, and irrational numbers relate to each other using a Venn diagram. The outer circle represents all real numbers. Inside, we have rational numbers on one side and irrational numbers on the other side. Every real number is either rational or irrational, but not both. Let's see how these numbers appear on the number line. Rational numbers can be plotted as points that correspond to fractions or terminating decimals. Irrational numbers fill in the gaps between rational numbers. In fact, between any two real numbers, there are infinitely many rational and irrational numbers. To summarize, real numbers consist of both rational and irrational numbers. Rational numbers can be written as fractions, while irrational numbers cannot. Together, they form the complete real number system that we use in mathematics. Welcome! Today we're going to learn about the Bodmer's rule, a fundamental principle in mathematics that helps us solve complex expressions in the correct order. Bodmer's stands for brackets, orders or powers, division, multiplication, addition, and subtraction. Let's solve a complex example using the Bodmer's rule. Our expression is 3 times for superscript 2 plus 2 times, 8 divided by 2 to 1, 5 plus 7. Let's solve this step by step. First, we'll solve what's inside the square brackets. 8 divided by 2 equals 4. Then subtract 1, giving us 3. Next, we handle powers. 4 squared equals 16. Now, we do multiplication inside the brackets. 2 times 3 equals 6. Next, we perform addition and subtraction inside the brackets from left to right. 16 plus 6 equals 22, minus 5 equals 17. Now we can do the multiplication outside the brackets. 3 times 17 equals 51. Finally, we add 7 to 51. Our final answer is 58. And that's how we use the Bodmer's rule to solve complex mathematical expressions. Remember to always follow the order. Brackets, orders, division, and multiplication from left to right, then addition and subtraction from left to right. Today we're going to learn about estimation, a valuable skill that helps us make quick, reasonable calculations in our daily lives. Let's start with a real-world example. Imagine you're shopping and have these items in your cart: a shirt for $23.99, pants for $49.95, and socks for $6.49. How can we quickly estimate the total? One estimation technique is rounding to the nearest convenient number. Let's round $23.99 to $24, $49.95 to $50, and $6.49 to $6.50. Now, the mental math becomes much easier. 24 plus 50 plus 650 gives us approximately $80.50. The actual total would have been $80.43. Our estimation was very close. Let's try another example. If a city has a population of 147,832 people, how might we express this as an estimate? We can round to different place values depending on our needs. Rounding to the nearest thousand gives us 148,000. To the nearest 10,000, 150,000. Or even to the nearest 100,000, 100,000. Here are some helpful tips for estimation. Round to numbers that are easy to work with, like multiples of 5 or 10. Consider the level of precision you need. Sometimes a rough estimate is sufficient. And remember that estimates should be reasonable and make sense in context. Estimation is a powerful tool that helps us make quick calculations and reasonable predictions. Practice estimating in your daily life, whether you're shopping, cooking, or solving math problems, and you'll become more confident with numbers.